Good morning, everyone, and welcome to the third day of CompsNet 2021. We are really honored and privileged to have Dr. Ken Duda from Arista Networks as our industry-invited speakers, starting things off this morning. And he's going to be talking about switching, routing, and security, integration, courtesy of Moore's Law. Ken is currently CTO and founder at Arista Networks. He's a pioneer in high-performance networking software and lead architect of Arista Networks EOS, a stateful modular operating system for all Arista Networks products. He is also the co-author of network virtualization specifications, including VXLAN with VMware and NVGRE with Microsoft. From 2005 to 2008, Ken was also the acting president of Arista Networks. Prior to joining Arista, Ken was the CTO at There.com, where he played a lead role in designing a real-time 3D distributed system that scaled to thousands of simultaneous users. Ken was also the first employee of Granite Systems and led the software development effort for the Catalyst 4000 product line after the acquisition by Cisco. Ken has 3 simultaneous engineering degrees from MIT and holds a PhD in computer science from Stanford University. And I've heard great things about Ken, and that in spite of being CTO and founder, he still writes a lot of code apparently. So I'm sure we're in for a great ride in the next 45 minutes. Ken, please do take over. I'm going to stop sharing my screen now.
Well, thank you, Ranjita, for that very kind introduction. And thanks to you and to Ashutosh and the whole CommsNet's team. I'm very grateful for the opportunity to speak to you today. And what I was hoping to do with this talk was really focus on the industry perspective of what's going on in the networking world. So, I've my background is computer science from Stanford, but I've been outside of the research community for a long time now. Like Ranjita said, I'm more of a programmer than a researcher to begin with, but have been building products now for many years. I actually first engineering office for back in 2004, out my bedroom door down the hall on the left here. So I haven't gotten very far in the last 6 years, but our company has come a tremendous distance, 7,000 customers, $2.5 billion of revenue. Very proud of the impact that we've been able to have in networking. So this talk will really be from that point of view, from the point of view of what's going on in the industry, what are the major technology trends that I see driving the industry, how do I see that shaping the way we build products, the kinds of products we build, and how customers take advantage of those products. So I hope this is an interesting and useful perspective for you, even if it's sort of outside of what the research community might ordinarily be focused on. And so the theme here is integration. If we rewind the clock here 20 years, think back to 2001. In 2001, there were many different types of devices. You had switches for your local area network that switched packets primarily at layer 2. Layer 3 switching was just starting, but very small tables, very high performance compared to the software routers of the time, but not suitable for any kind of scale application. Routers did routing, ran sophisticated protocols, customers VPNs, lots of different interface types, connecting networks over a wide area, over SONET, over frame relay, over ATM. Sniffers, we had whole catalogs of products for optical taps and getting the copies of the network traffic and funny kinds of transceivers to pull traffic into analysis devices. Security was always sort of a bolt-on or an afterthought or something that you put onto the side. You had firewalls to provide security, special purpose devices whose only function was to try to kind of somehow secure what was otherwise a very, let's just say, security wasn't the first thing on people's minds who are building the packet forwarding devices. We would refer to these networks as hard and crunchy on the outside, soft and chewy on the inside, because once you're inside one of these networks, you could do anything. You could get any kind of traffic from any machine to any other machine. And overlaying all of this was a network management system using protocols like SNMP to pull devices, pull out topology information, and provide some kind of a management view into this. So you have separate boxes, separate functions, all from separate vendors, and a big pile of pieces parts for customers to try to assemble into networks. And this is really not a great situation. First of all, look at security. Security needs to be integrated. We need security at every layer of the system. We need security to be designed in, to be front and center in our minds as we build our routing stacks, as we create our forwarding architectures, not bolted on the side, inserted into the middle, slapped on top. It's very ineffective to try to add security as an afterthought. And management is the same way. Network management has been an afterthought in our industry for far too long. And you can't do it. There's no practical way sitting outside the network to actually get the visibility into the state of the forwarding elements and the control over those forwarding elements that you need to provide an integrated management experience where you can do in-service box replacements, where you can roll out configuration changes incrementally, where you can really understand what's going on in the network. Visibility also, rather than tapping your switches and then pulling it off to the side, visibility as well should be integrated so you can track actual packets through the network, understand where they're experiencing latency, understand where you have routing loops and why, rather than trying to sort of reconstruct this all after the fact from network traces captured at a limited number of points. The other thing that we're seeing is more and more data center operators are service providers, especially within large enterprises, where the data center operators have many different contingencies and constituencies within their organizations that they need to serve. They need to provide virtual networks for different competing interests within their own organizations. So data center switches need to have service provider router features about route scale, about tunneling, about overlays, virtual private networks, all the cryptographic functions to secure traffic, the operational administrative management functions. And then conversely, service providers more and more are operating large data centers, providing cloud services to their customers. And these service provider switches need the data center features. They need to be able to terminate VPNs and then connect the enterprise into the cloud. We need to have traditional MPLS L3 VPN internetworking, interoperating with data centers class EVPN, and you need high performance service provider devices for internet access aggregation and peering, because as you all know, in this crazy pandemic world, bandwidth demand, whether it's sessions just like this one, whether it's your kids doing distance learning from home, whether it's media streaming, the bandwidth demands of the modern internet are driving service providers to require the data center sort of cost performance ratios that we're able to get. But I think that really the core message of all of this is that binding functions to a piece of sheet metal is a mistake. The top of rack switch in a tier 1 service provider data center has to terminate customer VPNs. When we've got the requirement list for one of these roles in one of the world's largest service provider data centers, and saw that the top of rack switch had to terminate L3 VPN, had to run targeted LDP to set up MPLS pseudo wires from a data center switch, what's going on? Well, this is all about how do they interconnect VMs running in a rack in a data center into customer VPNs, right? So it no longer makes sense to structure the network as separate boxes providing these separate functions, because you need to terminate one type of network and enter another type of network in any class device, thanks to virtualization, thanks to overlays, and thanks to the performance requirements of getting traffic, especially streaming media, in and out of these virtual deployments. So we're seeing that the traditional way the industry has assigned different functions to different types of devices is just sort of a fundamental mistake in the architecture. And fortunately, we have some powerful forces helping us out here. Number one is Moore's Law. If you go back to 2001, again, look 20 years back into that day of like separate boxes with separate functions, we got maybe 10 million transistors onto a chip. Here we are 20 years later, we're getting 10 billion transistors onto a chip, right? So a factor of 1,000 changes what you can do. And we see that in along two dimensions. One is the functionality. With so many more gates in switching ASICs, we have massive table scale. We have the ability of a data center class piece of silicon to do deep MPLS operations. We have multi-stage access lists where you can run the packet through a whole cascade of TCAMs to first classify the source address, then classify the destination address, then do a policy lookup to see if that source can talk to that destination, that sort of thing. We have cryptography functions now integrated into silicon, standard off-the-shelf silicon with a full AES 256 implementing MACsec and IPsec. We have deep programmability in these chips so that vendors like Arista can take off-the-shelf merchant silicon and create whole new header parsing rewrite operations supporting, among other things, in-band network telemetry, which I'll talk about in more detail in a few minutes. So those are some of the key ASIC advances we've seen. And then going along with that are much larger table sizes. And this shows the size of the layer 3 table, talking here about IPv4 unicast forwarding, in our sort of what we regard as the sort of top of the line, but still mass market, sort of cost-effective switch silicon from the leading silicon manufacturer. In 2010, the top-of-the-line chip had 16,000 IP forwarding entries, which was enough to cover a standard enterprise data center as long as you can default route out of it. By 2013, we could do 300K. And this enabled Arista to succeed in the cloud data center, talking about companies like Microsoft, at sort of massive scale with the larger routing table. By 2016, we have 2.2 million routes in standard merchant silicon. And that changes the whole game because now you can hold multiple copies of the entire internet routing table and be a fully functioning internet peering router. And here, getting a little more closer to the present, in 2019, we started shipping devices with 4 million routes, which is enough for carrier VPNs. So each of these sort of turns of the crank of Moore's law enables merchant silicon-based networking devices to reach whole new market segments. And that's what enables the kind of integration I'm going to talk about in a few minutes of all the features into one device and operating system framework. The second major force is the cloud. And what the cloud has done for networking is enabled network vendors to offer services that go beyond the individual devices. And so whether it's management or security or network visibility, companies like Arista are now able to offer cloud services to our customers so that they can, this enables us to provide more than boxes, but actually whole network management functions, visibility and security functions. So I'll talk in more detail about that. But this has been a major enabler for us to increase the value of what we're able to deliver to our customers. So here we are in 2021, and what you'll notice is that not only do switches switch, now switches can route. And by route, I don't just mean layer 3 forward, because that's been around for a while, but I mean all the functions of a high-end service provider router, the MPLS stack, the VPNs, the multi-layer multi-protocol BGP, the multicast MVPN, the IPv4, IPv6 interoperability, all the fast reroute and all the MPLS features, all the OAM features. We have all of that in the same devices. These same devices can also capture traffic and steer that traffic to analysis devices, modify the traffic so that it can be de-encapsulated, it can be timestamped, it can be sliced, providing a full visibility suite as well. Switches plus the cloud can manage the network also. And managing the network here doesn't just mean SNMP polling, monitoring link status, and monitoring counters. Managing means every aspect of the life cycle, from planning out a deployment, deploying the switches, configuring them all, replacing them when they fail, in-service upgrades of the software, in-service rollout of configuration changes. All of those things are provided by an integrated management stack, along with compliance, bug tracking, security advisory alerts. It's a complete deployment lifecycle management system, cloud-based. Switches plus the cloud can secure the network as well. And security has many dimensions. I will talk more about them in a few minutes. And finally, switches aren't just forwarding at layer 2 and layer 3 anymore. Switches also forward at layer 1. And I'll talk about that more. But by integrating all of these functions into one device, running one software stack, managed by one cloud management system, it's a fundamentally better integrated solution for the customer. Building it is a bit of a challenge. I'll talk more about that in a minute as well. So routing has been integrated. As I mentioned, switches now route. This is just sort of a list of some of the features that are required. I'm not going to spend a lot of time on this, but these are features that you probably didn't see, or you certainly didn't see in data center switches 10 years ago, and these are now widely available in data center switches. Data path monitoring has also been integrated. And so data path monitoring actually has a couple of different dimensions. So back in the olden days, of course, you just span your ports or you get optical taps and send it off to network packet brokers to do all of the actual work. That's all now been integrated in so that you can, from the switch, you can, of course, do port mirroring or optical taps if you want, but my preference is to mirror into GRE tunnels and tunnel the captured traffic out to a separate analysis fabric, which is the same devices running special forwarding rules. Because once captured traffic hits your analysis fabric, you no longer forward the traffic based on the actual addresses in the packets, obviously. You forward it based on some kind of a session identifier, some kind of a tag that steers the traffic to the correct set of tools for analysis, be they network VCRs and recorders, protocol reconstruction, network logging. There's just a whole sort of plethora of analysis tools that customers can then connect to the analysis fabric. We also have flow tracking. So we create flow records on chip in hardware and then stream those out to IPFix collectors. And then finally, I'm going to talk a little bit more about in-band network telemetry, because this is the newest form of visibility we've been able to offer as an industry to our customers. It's sort of an interesting technical area. In-band network telemetry, the kind of popular attempt number one was to define a zone, a telemetry-aware zone, so it's the green zone here in this picture, where all of the switches in that zone understand how to do the in-band telemetry. So when an outside packet enters the zone, step one, it enters the switch in step two, the ingress switch adds an in-band network telemetry trailer to the packet, which contains space for each switch along the path to update that packet with a record of which switch it passed through, which interface it came in, which interface it's going out, how long it spent in queue, a picosecond granular PTP-based timestamp on the packet, all that sort of stuff. So hop by hop, the switch gets this trailer extended, and then at the egress point, the egress switch strips and collects all of this data and somehow streams it out or does whatever it does with the actual data, and then forwards the original frame. The problem with this approach is that it's undeployable because it requires this one zone where all of the switches speak this magical language. And one of the things I learned the hard way with VXLAN is that changing protocol architectures takes like a decade. I mean, it's really hard to get the industry to move in this sort of a way because of the weight of the installed base, the need for all of your intermediate tools to understand the packet formats. It takes it's a slow process. So we believe there's a much better solution here, which is postcards, where your in-band network telemetry is purely a hop-by-hop function, not requiring any zone or region of the network that supports it, where the switches in your network that support this are all configured with a policy for determining which packets should be measured. And usually that policy is some combination of matching on header fields and then taking a hash and selecting a subset of the hashes. And that way every packet along the path, every switch along the path that the packet takes will make the same decision about whether or not that particular packet is being traced. And if it is being traced, then the switch sends a postcard to the collection station, probably in the cloud. So the postcard is GRE tunneled, and it includes some information about the traffic that's passing through, and about the experience that traffic had as it was passing through. How deep is the buffer? How long did it spend in queuing delay? What was the timestamp of ingress? What was the timestamp of egress? What are the ingress and egress ports? And then even a truncated copy of some of the data in the packet. And then the analysis station can put this all together and give you the GUI and the time log and the alerts and the capacity planning, and all those features then get built on top of these postcards. And to me, I think this is the direction that the industry is going to take on in-band network telemetry here. So that's on the visibility side. On the management side, we've integrated management into all of our devices, and each device streams the full device state from the device into the cloud. And this streaming all of the state means every state change, every control plane table that gets updated, every MAC address you learn, every neighbor ARP entry that you resolve, every IGMP packet that you snoop, every control plane state change gets, and also for the hardware, the physical layer state, and as well as management state, all gets streamed into a time series database. We use Kafka and HBase for this. to a Kafka queue, goes to an H-based time series, and then the streamed computation language then digests that data, creates statistical summaries, it correlates events, and figures out a link down over here and a link down over there. Well, that's the same link, and here's a link down cause. All that sort of analysis is done in a stream computation layer on which applications on top give the customer the visibility and control of their overall network. And like I said before, this isn't just telemetry. This is also all of the device lifecycle functions in terms of configuring devices, changing their configurations, upgrading their software, doing this all in service according to a plan with pre-network, pre-upgrade checks, post-upgrade checks, validation that the network is behaving properly. All of that sort of workflow is captured in these cloud deployments. And there's really no way to bolt this on top because people have tried this. How many startups can you think of that went into to sort of start tackling the problem of how do we manage the whole network? How do we give the customer an integrated experience across all of this menagerie of vendors and all their different operating systems? And it's never succeeded. They always wind up getting acquired by whichever of the major vendors feels they need a management solution the most, right? So I believe that integrating the management stack between the vendor's devices and the vendor's cloud deployment is the future. And then to provide a whole network view, not just a single vendor's view, these management deployments need to exchange state. And that's what you see on the slide here, where we believe that OpenConfig is a suitable format for streaming some of the key network state in a sort of open standards and kind of lowest common denominator sort of way to enable a single pane of glass, or at least a nice stained glass window, where the different parts of your network are integrated together and to give you that sort of overall starting point to drill in. So integrating management, I think, is a major trend that we've seen over the last 20 years enabled by cloud and by the higher function of these devices. Security is a major integration point as we've integrated security much more into layer 2-3 switching. I mentioned multi-stage ACLs already. We've also developed segmentation groups, which enables the customer to place endpoints into segments and then create policies for which segments are allowed to communicate with which other segments. There's also MACsec and IPsec, as I mentioned, and finally network detection and response. Some more on segmentation groups. You divide your network up into different types of devices that are allowed to communicate or not allowed to communicate, and then the switches enforce those segmentation boundaries. Those boundaries are without regard to addressing. So many traditional segmentation approaches require that segments are defined by addressing boundaries, whether they're VLANs or IP subnets, with TCAM rules to match on blocks of IP addresses and implement policy that way. Problem is, tying addressing to the right to communicate is the wrong thing to do from the customer's point of view, because when people show up on the campus with their devices, their laptops with Wi-Fi, their address is assigned based on where they are, not who they are. And so what you need is addressing based on location, segmentation based on identity. And so I think this is a fundamentally better way to not allow communication. I mean, so much of the early world of switching was focused on allowing communication. It took us as an industry a little while to realize that not allowing communication is also very important, and that's what we're doing with segmentation. With MACsec and IPsec, as I mentioned, this is now integrated into off-the-shelf silicon. We have line rate tunnel encryption engines. It applies AES 256 to the data stream. This has zero performance cost. It's full line rate, and we support various encapsulations. So there's MACsec, there's IPsec, support for this for VXLAN and MPLS as well, because the hardware crypto engines are configurable about which regions of the packet they encrypt and what they do with the signatures. So I think this is really going to change the way that people deploy crypto in their networks. Today, crypto is pretty much only used where you feel you really need it, where you've got remote employees coming in over the internet. You'll use an IPsec VPN or something like that. But crypto is generally regarded as too expensive for ordinary kind of day-to-day use. But I think essentially this is free now to have these capabilities in hardware. We're going to see companies changing their InfoSec requirements and require either MACsec or IPsec at every layer of their network, from their IDFs into their data centers, because why would you take this risk when there's no need to? So I think we'll have a whole upgrade cycle driven around the need for security, crypto privacy at each layer of the network. Network detection and response is also a very interesting area. This is sort of a rethinking of the intrusion detection systems where the network needs to always be watching itself. So simply preventing communication and preventing eavesdropping is not enough. You also need to always be watching what are people doing with your network. So when they're doing something they're not supposed to be doing, you discover that at the earliest possible time and have all the data that you need to understand who did what when, what data was exposed, what data was modified, what data was exfiltrated, right? And so what you need is integrated sensors at every layer of your network, extracting traffic, summarizing it and sending it to the cloud, where you have an ongoing system always being trained, always being updated with the latest virus signatures and the latest attack threat vectors, but also creating archival records of everything that's happening, so that you can query this later and go back and figure out what broke when, who did what, and what are we going to do about it. So all of those functions are enabled by integrating the data extraction and analysis functions into the switches, and then conveying to the cloud just the summaries, because there's far too much traffic, of course, going through these switches to send a copy of everything, right? So you have to divide the problem up between the sensor side and the nucleus side. Another really exciting development to me is the integration of layer 1 switching into standard Ethernet switches. And layer 1 switching means instead of switching packets, we're just switching serial lanes. So the customer says anything that comes in serial lane number 1 should go out serial lane number 7. And when you're controlling switching at that very low level, you can get incredibly low latencies. And you know who cares about this are the financial traders. The people doing these very high performance trading systems are able to bring market data into their servers with a 7 nanosecond replication latency through the switch. And this is just, I think getting to the point where we've reached zero. It's in terms of the if you think about a minimum size packet at 10 gigabit Ethernet, it's 672 bit times, right? So 67 nanoseconds from beginning to end of the packet. A 7 nanosecond latency is essentially zero, even to a high frequency trader. But then this is not just a layer 1 device, because when you're doing your risk analysis and your order entry and things like that, that needs to go through a standard routing stack. And before the integration of layer 1 switching, customers had to use very expensive trading colo space to hold both layer 1 crosspoint devices and then a separate layer 2-3 switch. We've now been able to integrate that into a single platform. So traffic that needs to be switched at layer 2 or layer 3 gets crosspoint steered to the ASIC. The forwarding decision and rewrite happens there, and then the crosspoint steers it back to the front panel port. Whereas traffic that can be cut through at layer 1 goes straight through the crosspoint. And this is a really a dramatic improvement for our high-frequency trading customers, which is about a $200 million market. So it's not huge. It's maybe 1% of the overall Ethernet market, but they're a fun crew to work with. And so it's where Arista really got its start. And so we always enjoy being able to maintain our edge on that particular market segment. There's another dimension of layer 1 forwarding, which is optical. And you're probably well aware of optical line systems that wavelength switch. And we have now integrated optical line switching into layer 1, 2, 3 switches. So the picture shown here is an optical line system in a transceiver cage. The device there in the center marked OSFP-LS. That is actually an optical switch, and it goes into, really it's a MUX, and it goes into a transceiver slot. And what comes into it are colored wavelengths. So if you can see in the middle ports on the left-hand side, the ones that are white are all software tunable single channel transceivers at 400 gig. So through software, you can adjust the wavelength that particular transceiver is using. Those wavelengths come out all different colors and go into the optical the colorless mux demux shown there is like a little pencil-shaped thing. And then that goes into the optical line system, which then amplifies the signal and can send it, metro distances up to 120 kilometers. So basically between NFL cities. And then on the way back, the colored traffic simply goes to all of the ports, all 8 channels, and then each port simply selects the color that it's tuned to. So this gives you tremendous fiber utilization. 400 gig times 8 channels, 3.2 terabits out of your fiber, and without any of the very expensive and sometimes ornery and difficult to manage optical line system boxes that you may be used to in carrier optical transport networks. So this is another example of layer 1 forwarding getting integrated into standard layer 2-3 switches. So I hope you're by now convinced of the amount of integration that's going on, and you can only imagine the amount of challenge this creates for the networking industry. Integrating so many disparate functions is not easy. Our software is already very large, and it's with silicon evolving at a rapid rate, creating new drivers constantly, and then all these new features coming in at the same time, requires constant refactoring of our code. Implementing new software infrastructure pieces to scale out table management, or the rate of change of tables, or the way we need to handle fault tolerance of the new line of silicon, or whatever it is. How can you make all those changes, integrate all of these features, while providing the level of stability and quality that customers need from their networks? And the answer is better architecture, better testing, and at the heart of it, a better culture. On the, let's see, so I'm afraid actually I'm running out of time here, so maybe I'll try to fast forward here to the end. So one network operating system, one testing system, and then the importance of culture. Culture underlies everything that you do as a company. An engineering culture of doing the right thing is critical. And understanding that quality is your number one goal. It's more important than features, more important than platforms, and more important than schedules is critical. And having alignment between those cultural values from the engineering side to the business side is critical. And I feel very lucky to have the support of my CEO, who has never criticized me for missing a release date. As long as the software works, that's what counts. So I think I'm out of time here, so I will wrap it up here. I would love to take any questions if I have a few minutes.
Yeah, you do. You do. If you want to speak for another minute or two, we do have some time, but we have quite a few questions as well. So since you finished, maybe we can just go to the questions. Is that okay?
Sounds great.
All right. Thank you so much, Ken, for that great talk. I have about 10 questions, but I don't think we have time for that. So let me start with the questions that the audience have put in the Q&A box. Rajiv Shore from Yukidar has asked, you mentioned integrated security in the complex networks today. However, this complexity results in increasing the number of attack surfaces and attack vectors. So how does one really integrate security efficiently?
Well, let's see, the premise of the question is that increasing complexity increases attack surface. Well, let's see, I guess trying to think of an intelligent way to respond here. It is certainly true that networks have become very complex. That is a fact. And the complexity absolutely creates security risk. And that risk then has to be managed. So if your point is that networks are as complex as ever and that creates security problems, I agree 100%. And so then the question is, what do you do about that, right? Because the complexity itself is there to solve problems. I mean, these are real issues that you can't just ignore. The different parts of the financial services company have to be kept separate. The different customers of the service provider need to have their overlays transparent to the customer, but kept separate from the service provider's viewpoint. So the complexity in modern networks, at some level, I think we've actually seen some improvements in terms of, networks used to be a menagerie, a Noah's Ark of weird technologies, ATM, frame relay, SONET. You had X10 networks, X25 networks, and we've seen a tremendous convergence towards Ethernet, towards IP, towards MPLS. So I think in some dimensions, we actually have succeeded in simplifying the network where the diversity wasn't buying us anything. But I think that once you've accepted that a certain degree of complexity is inevitable to provide the kinds of services that networks need to provide, the right question to ask is, well, how do we do the best we can to secure all of that? And certainly when switching vendors are sort of ignoring security and saying, we're just going to forward all the things and we're going to let you worry about, isolation and protecting yourself in separate devices, that's not making things easier. And so I think that the way we can help here as a switching industry is by integrating security features into our devices as much as possible. I gave some examples of that, so maybe I'm not sure I understand the spirit of the question exactly, but some examples of how the switches can help with security is by encrypting the individual links with built-in MACsec and IPsec. It's by providing segmentation mechanisms so that customers can classify endpoints into segments, and then the switches simply prevent communication between those endpoints. And it's also by always monitoring and always watching what's going on in the network, analyzing that, and providing that data out to the cloud, where then the customer can be alerted when things are happening that aren't supposed to be, and as a platform for querying what's actually happening in the network to understand if things are happening that shouldn't be. So I think that while the situation is very challenging, and we're seeing, I think, an increased concern at the governmental level, at the level of our top financial customers, as well as in the popular attention, there's an increasing concern around security. I think we're doing, we're trying to help, let's put it that way. So I hope that answered the question.
Yeah, I think so. Ken, I had a follow-up question to that. So in research, there's a lot of work that has happened in network verification, of using formal methods to verify different protocols and also implementations. As a practitioner, do you see, and there are some startups also in this space, but as a practitioner, do you see this actually being used?
I have not seen much use of this. There's one company doing this that's gotten some attention, although I'm going to forget the name of it now.
Intentionate, I think. Yeah. But go on.
The problem I've always found with formal verification methods is that the scope of the verification problem is so broad, and it goes so much beyond a simple statement of the routing algorithm, and it encompasses just tons of implementation details around the way switch ASIC tables are programmed, and the way that in a multi-chip system, the way you sequence the programming of those tables, it's just very challenging. And so I haven't seen formal verification play a major role. There is one area where I expect we're going to see a lot more verification, if not formal verification, at least something of a similar spirit, maybe, which is, I've now forgotten the name. At Microsoft, internally it's called CrystalNet, but I've forgotten the name of the offering. It's a commercial offering now at Microsoft, which is a virtual replica of your physical network. It's really cool. So you end up running a whole bunch of instances of switch software in containers on a standard server VM farm. And so you can have thousands of these, because containers scale so well and they're all running the same software. And then you can't run a lot of traffic through it because it's a software data path, but you can validate that your configurations are basically sane, that your routing tables converge, that certain traffic that should make it through makes it through, certain traffic that shouldn't make it through gets blocked appropriately. And you can do I won't call it verification. It's not what any mathematician would mean by formal verification, but it is a way to do a deep sort of testing of configuration changes or topology changes or protocol changes without actually putting your production traffic at risk. So I think we'll see a lot more of that as we figure out how to integrate that sort of pre-flight testing of network changes in a way which is consumable to the enterprise and not just to the extremely technically sophisticated customers like Microsoft.
Mm-hmm. Thanks. Ashutosh asks the next question. Is intrusion detection integrated as part of the switch? Is traffic visibility impeded due to virtualization?
So it's two questions, I think. I'll just take them separately. I'm not sure if they're meant to be related. The intrusion detection is integrated, and so I think we've got this term network detection and response, which is sort of a generalization or an expansion of what's meant by intrusion detection. And so it's integrated not just in switches, because switches themselves lack the storage, the horsepower, and the full network view that you need to do a good job of intrusion detection or network detection and response more generally. So it ends up being a function that's divided between the switches themselves that perform a sensor function of capturing flow data, of capturing certain flows, of triggering on certain types of traffic, of creating statistical summaries, and sort of noticing when things are outside of scope and that sort of thing, and then conveying that information to a central analysis point where you can then retain data over a longer term, have much more memory and computing power, and you can apply machine learning algorithms and some of the AI stuff to sort of make some sense out of the flood of data that's coming in from the edges. So we're seeing network detection and response being a divided function, but integrated in the sense that it's provided by the switching vendor with function in the switches as well as function in cloud software. The second question was about virtualization and visibility. This has been a really interesting area. There's been a huge amount of drama in the industry as some of the leading networking players kind of battle it out with the leading virtualization players as if there's some big fight for control over the network. I have never been able to understand this viewpoint. I view that there are devices in the network with lots of ports. We're going to make those and do there what makes sense. There are also servers that are going to run software from one of the virtualization vendors. Let's do what makes sense there, and let's work together to provide the best overall solution for customers. So, for example, Arista worked closely with VMware and VXLAN and created the first hardware VXLAN implementation. And we did the first integration with the OVS DB from Nicira and VMware to provide a virtual to physical interface in physical switches for devices that didn't run the virtualization software. The switch could play that role of bringing traffic in and out of the overlay. And then we have interfaces into VMware's vCloud Director to get all the information about the virtual topologies, so we can tell you, as a switch operator, which VM is on which server, connected to which switch port, which VXLAN overlay is it in. So we can provide full visibility into the virtual topology in partnership with virtualization vendors. So we find it's much better to partner here than to fight. And we're not at all worried about losing visibility because the virtualization players gain nothing from creating an environment where network operators have lost visibility into their traffic. So they go out of their way to provide APIs, to provide an integrated management solution so that we can give our networking customers visibility into the virtual topologies. So I have no concerns with what Ashutosh is referring to there. And I think we're actually on a very good path as an industry, although with a fair amount more kicking and screaming from some of the other vendors than I feel was really warranted.
Thank you, Ken. I appreciate that.
Thanks. I think we have time for one quick question. So Rajiv asks, how is network system software evolving? For instance, SNMP, etc.
Maybe I missed. So SNMP, this is a management plane focused question?
I think so. I think that, I guess that's the way to construe that.
Yeah, so this is let's see, what's the right way to describe this? This has been an area of a lot of interest of mine, and frankly, a lot of frustration with the path that the industry has gone down here. There's been this emphasis on trying to standardize. So people talk about the planes of the network, right? You've got the data plane with Ethernet forwarding, IP forwarding, GRE tunnels, all that kind of good stuff. You've got the control plane with BGP, OSPF, ISIS. Then you've got the management plane, we say, but what is it actually? The COI, SNMP, how do those things make a plane? Those are just access methods for getting state in and out of a switch. But what's on the other side of that? How do you federate this thing? How do you build an overall system? Our data plane and control plane work really well, enabling customers to build overall networks out of these components to provide really advanced end-to-end features, right? But where's the management plane that does that? It's just like missing. And the problem is, I view that it's been kind of a lack of imagination on the part of vendors, combined with a business model problem. That if your business is shipping shiny metal boxes, how do you ship a management plane? Because fundamentally, I believe the right way to architect the management plane is what I showed in that figure. I kind of went through it a little fast, but let me bring it back up. And I hope this is responsive to the question here, which is this figure here, where the management plane is made of nodes, where this thing here, this cloud bubble, is a node in the management plane, not the devices themselves. The devices themselves are nodes in the control plane and the data plane, but the data is simply transmitted, conveyed into the cloud, where this cloud clump of compute and storage, this thing is the node in the management plane, which can then federate to other nodes in the management plane through state exchange. But instead of exchanging, IP reachability information like BGP does, you're exchanging management state, say via OpenConfig. So this is, I believe, the right way to build this. And you don't get here with SNMP, right? Like SNMP polling, you get a small handful of standardized MIBs, which are slow, and it just doesn't. What we've done here is we do state streaming. We stream every state change as it happens with coalescing. So if the network is thrashing and the states are changing more quickly than the cloud can receive them, we automatically coalesce those state changes so that you eventually get to the correct final state, even if you lose some intermediate transitions. And this sort of state replication or state streaming model is, I believe, the right foundation for the management plane. And unfortunately, SNMP, of course, doesn't provide this at all. But even OpenConfig, which is the more recent development in this area, OpenConfig, again, it's the same basic problem. It's a small set of standardized models that doesn't capture all the things that you need to truly manage a network. You don't get all the operational state of the hardware, transceiver temperatures, power supply voltages. You don't get the software upgrade features and the ability to roll out configuration changes incrementally, hitless. There's just a bunch of management functions that aren't captured through OpenConfig. So I don't see that direction as being a good direction for the industry. Look, there's a small number of companies, and Microsoft is among them. It's Microsoft, it's Google, you know who they are, that have invested tens or even hundreds of millions of dollars building their own full custom management stacks. And for them, OpenConfig is useful because it gives them a better way of getting a certain amount of state out of devices into their own full custom management plane.
Yeah.
Great. And Arista is very happy to support the cloud customers. They're among our biggest customers, as you probably know. But it's not a solution for the enterprise. The enterprise has no ability to take Microsoft, proprietary network management stacks or Google's or whoever's and run them. The OpenConfig is, again, just a pile of parts. So they don't know what to do with it.
Sorry, Ken, I have to cut you off there because we're running out of time. But no. This is great. I wish we could continue, but we are a little over time. So I really want to thank you so much for this fabulous talk. And there are a bunch of other questions as well on this channel. If you can stay, maybe the student volunteer who's here can help you navigate through those questions. And I'm sharing my slides again just to show a plaque that we're going to be shipping to you physically to your mail ID. Thank you very much again. This talk was very informative and enlightening. Thanks very much.
Thank you for the kind words. I really appreciate the opportunity. Oh my goodness, that's very kind. Thank you very much. I appreciate it.
All right. Thanks.
Bye, Ken.